Okay. So the last part of special topic G comes down to being able to identify 6 fundamental reaction types in a given mechanism of these organometallic reactions. Now, again, you don't have to know the actual mechanisms of these reactions, but if we give you a step where you have reactants, something over the arrow, a product, you should be able to identify it as either oxidative addition, reductive elimination, ligand association, ligand dissociation, ligand insertion, or ligand deinsertion. Now, first of all, let's go about defining them and how can we tell them apart. Well, the main thing that's going to differentiate each of these reaction types is what happens to the oxidation state of the metal and the total number of ligands on that metal. So let's start with oxidative addition. I'm going to abbreviate it, oxidative addition. So let's say we just have palladium. Nothing special about this palladium, it has nothing attached to it, and so its starting oxidation state is +0 because it doesn't have any negatively contributing ligands. Its net charge is 0, so its oxidation state is 0. And now over the arrow, you're going to see something like an H2 coming in. This is one common example. And the other common example you'll see often is a benzene ring, or usually a benzene ring with a halogen on it. In this case, I'm using bromine, but any halogen will do. And for the record, whenever you see an arrow converging onto your reaction arrow like this, that just means you're adding something. So hydrogen gas is coming into the mix to react with this as it goes forward. And now the product you should expect as a result of this is palladium with 2 hydrogens. Again, you wouldn't have to know what this is supposed to be, but we would give you this, this, and this, and ask you, well, what happened here? And the product of this arrow, if it reacts with palladium, would be palladium with now a bromine on it and a benzene on it. And now the question is, well, what happened to the total number of ligands and the oxidation state of our metal? So let's start with oxidation state. The oxidation state of this metal, well, both bromine and carbon contribute negative charges, right? Hydrogen, halogens, and carbons are all worth a -1. So in this case, the palladium that got 2 hydrogens, well, that's 1 minus 1 there, 1 minus 1 there. So we know that the palladium must have an oxidation state of +2. So the oxidation state started at 0 and went to +2. So the oxidation state increased. The metal was oxidized. Same deal with this palladium. Carbon is worth -1. Bromine is worth -1. So the palladium must be +2. The oxidation state increased by +2. So we oxidize the metal by adding something to it, hence the name oxidative addition. So what we can summarize here is for oxidative addition, the oxidation state will increase and the total number of ligands will also increase. Okay? Now what about reductive elimination? In the case of reductive elimination, let's say we have a palladium with HBr, or a hydrogen and a bromine on it, and we go to just a palladium without anything on it. And over the arrow you see this, HBr is leaving. And again, this is kind of the opposite of what I had with the H2 coming in. This just means something is leaving. As the palladium goes here, something is coming off of it, in this case HBr. And then another example you will see sometimes is, let's say we have PD, and then we have a carbon chain like this. Let me grab a carbon chain like that, and then we'll just add in a hydrogen, and that's good enough. A carbon chain and a hydrogen. So what would happen? And then over the arrow you see, let me make this 2 carbons rather. So 2 carbons on the palladium, and then over the arrow you see CH3 leaving. And you get palladium again, just palladium. Well, let's look at each of these 2 things and see what it is. So we had a palladium with 2 ligands attached to it, and what was its oxidation state? We had -1 from the bromine, -1 from the hydrogen, so the palladium must have been a +2 oxidation state. And now the palladium has nothing attached to it, no negatively contributing ligands, so its oxidation state must be 0. Here we have a palladium that is also +2 oxidation state because a carbon and a hydrogen each give -1, so +2 oxidation. And now we're having 2 carbons leave, or we're having these 2 carbons leave, and notice this is a CH2 over here, right? So this hydrogen must have also joined one of those two carbons to make it CH3, so we lost 2 ligands again. And now we have a oxidation state of also 0. So in this case, we reduced the oxidation state. We decreased the oxidation state by removing, or in this case, eliminating ligands. So this is an example of reductive elimination, because we reduced the oxidation state and also eliminated ligands. Okay, so based on that, we can say that for reductive elimination, the oxidation state will decrease, and the total number of ligands will increase. Will also decrease. Okay, and that's the difference between oxidative addition and reductive elimination. They're basically the opposite of each other. Now, one really important point to make is only oxidative addition and reductive elimination affect oxidation state. The remaining reactions that have ligand in the name do not affect oxidation state. So in this chart that I had written out, oxidation state will never change, so I'm just going to erase that. The only thing that will change is the number of ligands attached, and we'll be able to differentiate them based on how those ligands attached. Let's start with ligand dissociation and association, because those are the easier of the two to recognize. So let's start with ligand dissociation. There are 2 common ways you're going to see ligand dissociation. So let's just start with our good old palladium again. And over the arrow, you're going to see a PPH3 coming in. Okay? So just some neutrally contributing ligand adding to the palladium. So PD now with a PPH3 on it. Now let me ask you, did the oxidation state change? It did not, because PPH3 does not contribute a net charge on the, or does not have a charge associated with it like hydrogen, carbon, or halogens. So the oxidation state here is 0, and the oxidation state here is still 0. All I did was I added a ligand to the metal, and that's all that happened. So over the arrow, I see a ligand coming in. So this is an example of ligand association, because a ligand is now associating with my metal. Another example of ligand association is, well, just any other kind of neutrally contributing ligand. So over this arrow could be C triple bond O, for example, CO. If you see that over the arrow adding to your palladium and you get this PdCO, well, that's still ligand association, because I had an oxidation state of 0 and I still have an oxidation state of 0. All I did was add a ligand that was over the arrow. The weirdest thing you'll see from ligand association is this, where over the arrow coming in is a C double bond C. And what you get at the end is now that palladium has a bond, not to the carbons of that double bond, but to the actual double bond itself. So what this says is the palladium is not directly attached to either of these 2 carbons, but it is associated with the pi electrons of the double bond. They're not directly attached, so these carbons do not affect the oxidation state. If this was a single bond to one of the ends of that double bond, then that would affect the oxidation state, because now you actually have a carbon bond. Here it's not the case, so this is still a case of oxidation state of 0, oxidation state of 0, so all I did was associate a double bond with the metal. This is a third example of ligand association. So these are the most common ways you're going to see it, but again, as long as oxidation state stays the same and all you're doing is taking something over the arrow and sticking it onto the metal, that will be that will be ligand association. Ligand dissociation, let's actually go to this chart then. So all that ligand association does is it increases the total number of ligands. Now, what about ligand dissociation? It's basically the opposite of this. So, I probably shouldn't have erased those actually. If we, for example, let's start with this. If we have a metal with an oxidation state of 0 and some ligand leaves, so let's switch to, you know what, we'll just start from scratch. So let's say we have PdPPH3. Okay, so oxidation state of 0 and 1 ligand. And then we see over the arrow something's leaving, and that thing that's leaving is our PPH3. Well, all I did was remove a ligand from my metal, but I did not affect the oxidation state. The oxidation state remains 0. So this is your first example of ligand dissociation. The ligand has removed itself from the metal without affecting the oxidation state. And then I'm basically going to be redrawing what I just did for association, but the opposite. So PD with a CO on it, and then we see the CO leaving. Well, that's still Ligand dissociation because the palladium has still 0 oxidation state, 0 oxidation state, and I removed the ligand. And then the weird one with the double bond associated with the metal, well, that doesn't change anything either. You're still seeing the double bond leave in this example, so you should have palladium. But since that double bond does not have a carbon directly attached to the metal, this is still an oxidation state of 0, and this is still an oxidation state of 0. So these are your examples of ligand dissociation. Okay? So in the case of ligand dissociation, the total number of ligands will decrease. Okay? And so these first 4 are probably the most straightforward. Ligand insertion and ligand deinsertion are the weird ones. They're not so straightforward as just adding something onto the metal or removing something from the metal. They do something a little weird and special. So let's start with ligand insertion. Based on the name, you might think, well, ligand insertion, how can I tell that from association? Because based on the name, wouldn't that just mean I'm adding something onto the metal, I'm inserting something onto the metal? Well, it's actually not the metal that you're inserting something into. And more on that once I write something out. So ligand insertion. Okay. So let's give that associated double bond again. So we have this. I'm going to add a couple things onto the metal just for completion's sake. We'll have a hydrogen there, and a ppH3 for fun. This won't really change anything. I'm just adding some ligands so it looks a little more complex. Okay. Now over the arrow, you're not going to see anything. And then as a product, you're going to see your palladium with the ppH3 untouched. And you still have a hydrogen, but now instead of having an associated double bond, you're going to have an actual carbon attached to the palladium. You're going to have this. So let's start by looking at what happened. Let's start by counting the oxidation state. I have an oxidation state on this metal of, well, each hydrogen contributes -1. This double bond does not affect anything because it's not attached directly, the carbons are not directly attached to the metal. So I have an oxidation state of +2. This metal has a hydrogen that contributes to -1, and now we have a carbon that is directly attached to that metal, so it also contributes -1. The oxidation state is still +2. So the oxidation state didn't change. What did change though? Well, clearly the double bond is now attached to the metal and it's not a double bond anymore, but notice your hydrogen count. We had 2 hydrogens starting out here and we lost 1 here. Or really, what happened to that hydrogen that went missing? Remember on this double bond, well, the end of the double bond just has 2 hydrogens each. But now look at your single bond. On this end you have 2 hydrogens, but how many hydrogens do you have on this end over here? You have 3. What happened is one of these 2 hydrogens inserted itself onto the double bond so the double bond could attach to the metal. So ligand insertion isn't just adding something to the metal, it's actually taking 2 separate ligands and fusing them together into one. So what you're doing is you're inserting the hydrogen onto another ligand, not onto the metal. So what happened is the total number of ligands in a ligand insertion actually decreased by 1. Because you took 2, combined them into 1, and now that one thing is on the metal rather than the former. So we were saying ligand insertion, you end up fusing 2 ligands together and combining them into 1. So we started from a double bond and a hydrogen, and now they're a single bond with an extra hydrogen on it. So the total number of ligands decreased because we took 2 and combined them into 1. But the oxidation state stayed the same. And that's the gist of ligand insertion, although there's one other way you can see it commonly. And that is, let's give you a palladium, let's stick on a ppH3 for fun, not going to do anything. I don't think it really does anything for our purposes in this course. Let's put a CH3 and a CO. Okay? Now I'm going to rewrite this CH3 in red because it's important. And now, again over the arrow, you're going to see nothing. But when you go to your product, you're going to have that palladium, you're going to have that ppH3 untouched, but you will now see a carbon, double bond oxygen, and that red CH3 So what happened here was you had a C triple bond O, right? CO looks like this, C triple bond O. And you ended up kind of pinching these two together. This carbon attaches to the carbon of the oxygen. And they fuse together, breaking the bond between the palladium. So you decrease the total ligands on your metal by 1. But what about the oxidation state? Did that change? Well, this palladium, the only thing that contributes a negative charge is the CH3, that carbon, because C triple bond O is neutral. Phosphorus is neutral, but carbon is not. Carbon gives a -1, so our oxidation state is +1. Here, we also have a carbon directly attached to the metal. And again, phosphorus does not affect the charge or the oxidation state, so we have a +1 oxidation state again. So in both structures, the oxidation states stayed the same, but the way the ligands were attached is different. We took 2 ligands and fused them into 1, decreasing the total number of ligands by 1. So again, that's what happens in ligand insertion. Now ligand deinsertion is basically the opposite. You take 1 ligand and you split it into 2. Now the thing about ligand deinsertion, if you look through old exams and practice problems, you're going to have a lot of trouble finding examples of this because it kind of doesn't really happen that often. And so if we ever make you have to identify it, it's going to be a custom tailored problem just for you guys to make it feel special. But basically, as far as I could think of, it's just going to be the reverse of this. So if you ever see a carbon double bond with a double bond O and a CH3, and you split that apart, and you go from this to this, well, that must be ligand deinsertion, because what I did was I took 1 ligand and split it into 2 separate ligands, but the oxidation state stayed the same. And again, ligand deinsertion, I took 1 ligand and split it apart into 2. So in this case, it was a carbon-carbon single bond, that is now a carbon-carbon double bond, and now we have an extra hydrogen on the metal as well. So for ligand deinsertion, the total ligands will increase by 1 because you took 1 ligand and now you split it into 2, so you have an extra ligand from what you started with. And that's the general gist of the reaction type that you have to be familiar with for this exam and for special topic G in general.